que hoy tiene un invitado de lujo. Tenemos al profesor Artur Avila, profesor en IMPA y en CNRS. Y bueno, no sé, estábamos Pierre Julio y yo organizando el coloquio y pensábamos si era preciso realizar una tarjeta de presentación del invitado, y yo creo que no va a ser ni siquiera preciso. Todos conocemos la brillante trayectoria matemática del profesor Ávila, y pues en ese caso a nosotros casi nos resta simplemente recordar el título de la charla. Bueno, muy obrigado, profesor Ávila. And the title of the talk is Almost Reducibility, right? Isn't it? Okay, thank you very much. Whenever you want.
Thanks for the invitation. I came already twice to Madrid, but it's the first time that I'm going to speak here. It's just a general talk about a subject that I've been working in several aspects of for many years. So we're going to try to present in a broader context and talk about some situations where it has been advanced more concretely, and mention some things that are currently in development. So a lot of this work has been done with some friends of mine, particularly more recently with Artur Avila. So the talk is about almost reducibility, but let us see what is what I understand by reducibility here. So, well, the topic, well, it's a general audience, so topics dynamical systems. So we were interested on evolution in time of some system, and there are several aspects that that you can be concerned here. We are interested on aspects related to mostly quasi-periodicity, and it stands initially from a situation that was first considered with Kolmogorov. So the aspects that were initially interested relate to what's called the KAM theory. So which I present in a very simplified way. So basically, KM theory was introduced by Kolmogorov when he was interested on problems such as the stability of the solar system or general motions in mechanics. And a typical situation, I'm not going to describe in general, would be already simplified, was what was considered by Arnold. So he considers a map of the circle. So here, so it's just from the torus, so one dimension to itself, and he considers a diffeomorphism, so an orientation preserving. And in his context, I'm not going to be emphasizing all the time the regularity properties, but by Arnold, it was the case of an analytic map. And the simplest kind of map that you could consider would be there are translations. So f of x equals x plus alpha, for instance, and so those are basic models. So that's the the circle, of course, has a group structure, and here are the translation by elements of this group. So this kind of motion, so there are going to be two cases when alpha is rational and you be periodic motion, and in general it will be when alpha is irrational, you're going to get a quasi-periodic motion. So so this is the simplest. So we can study it from a group theoretical point of view how it it behaves. And so let's assume that you understand completely this kind of simple motions. And now you're going to be interested in kind of more general situation. And what can you say about this? And the initial work in this direction was done by Poincaré, who showed what? So he considers general situation. Just assume that F is homeomorphism. And then he says that you can always associate a number so that which is called the rotation number. So there exists something called the rotation number. You can call it alpha in this case, which is a number that could be rational or irrational again. And then there was a basic dichotomy that if alpha was rational, so what's this rotation number? Essentially, just that it's not how it's defined. You start with the circle from T to T. You can lift it up to R. And then here you have some F, and then it's covered by some F tilde. And then you're going to have basically, as you maps, you take a point in R, and you apply several times F tilde. You're going to have the following thing, that F tilde n of x minus x divided by n, this converges to some number alpha. So there is some, as you kind of iterate map, so that it kind of moves by some kind of thing that depends on x, and then it moves again and moves again. But when you kind of let time pass, you make it longer and longer, it is stabilized, and then in average, you're always moving by some kind of fixed quantity to either to the right or to the left, and so on. So that gives you the rotation number. So this rotation number can be a rational number, and this implies that all trajectories are asymptotic to periodic points. Or alpha is and then there are no periodic points, and in fact the dynamics resembles that one that's given by the rigid translation in the sense that you can there is a semi-conjugacy, which you can write like this. So here there was the map F, and here x plus alpha. That once you move by F, moving by x plus alpha up to a kind of map here that appears that you call, let's say, H, and H is a map that's a monotonic continuous surjection. So there might be some intervals of points that collapse to a single point. So you could, so it's not kind of homeomorphism of the circle, but up to this, it is essentially like homeomorphism. You can think that you had the motion of points in the circle, then you explode some trajectories to intervals. That's the general construction. And what, so that was his initial theorem. Then, of course, at the level of homeomorphisms, this can really happen that you have this kind of intervals that collapse to points, because you can just kind of introduce those intervals. Then later, Danjois showed that this may happen even if you have not homeomorphisms, but just a diffeomorphism of the circle. This can also happen if the regularity is not large enough. On the other hand, if it is sufficiently regular, then there is a theorem. So if F is regular, like C2, then H is homeomorphism. So that this kind of collapse doesn't happen. So you see that the dynamics, so what happens for this kind of map, general map here with an irrational rotation number, is topologically the same as what happened to a single to a fixed basic element, the kind of basic model. That's the translation. Now, so what does this mean that you have the same, even by the combinatorial theory of Poincaré? It says that orbits are the same in which sense? Well, according to Poincaré, basically, it's just taking care of combinatorics. So if you look at orbits of F, so it's a sequence of points, first, second, third, and so on. Well, maybe it starts with 0. And then, and so on, then it's going to have some bunch of positions of these orbits. And here there is x plus alpha, and then there will be a bunch of positions of these orbits here, 0, 1, 2, 3, 4. So that sequence of this. And Poincaré says that the positions of those orbits are the same here and here. So they are in the same order, like between 4 and 1, there is 0, and so on. So so Poincaré theory gives the combinatorics of this. Danjois, well, this theorem here, when you have that it is in fact an homeomorphism, is giving you a little bit more. Not only it is going to be essentially distributed in the same combinatorics, well, but here in the case of the translation, it gets denser and denser, so it kind of fills the circle. And here it's also going to fill the circle, and just kind of you're just kind of changing a little bit the positions, but kind of not drastic way. So there's the same topology from one place to the other. And the next step would be kind of a more detailed description of how the orbits are. Would be so to understand this, it would be kind of an improvement. It's a successful improvement of the regularity of this. So if you know that, for instance, H would be C1, let us say, it means that if you look very kind of locally what's happening, then you're going to have like a little interval located somewhere. You explode it to just to see it better, to a big interval. And then, of course, initially there's just one point here that at some point appeared, and then a long time later, a new orbit appears. So here it was the first point, let's say. Then here at some other point, the map 1017 is here. And then at some other moment, somewhat else appears here, and so on, some big iterates. And then here you have the same for the x, for the translation. So this is for f, and this is for x plus alpha. And then you know that there are going to be orbits like this in some intervals. And basically this picture and this picture, they would be related essentially by an affine map. So the relative positions is kind of is the same, but the distance, like if you have those kind of shapes here, they are going to correspond more precisely. So like just by some small distortion from here to here. So once you look in kind of small scale, you have the same metric structure for this, right? Just needs to look closer and closer. So this kind of more detailed information about how things are getting organized is kind of captured in this kind of regularity of H. But this was not following from Danjois theory, and that's what kind of comes into to the analysis of this. In fact, it was possible to show, I don't remember who gets first counterexamples. That's even that's not always the case. Even if you assume now that, like here for this theorem, you don't assume anything more about f except that you have some regularity. Then it's possible to show that you can assume arbitrarily much regularity. Let's say that you have an analytic map, and still you don't improve on getting an homeomorphism. You don't get something C1 or whatever. So so the theorem that would be proved by Arnold was like this. So made some initial contribution in this direction, which was the following. So suppose that f analytic and assume also, and let's assume that you are kind of starting in a kind of perturbative situation. So it has the form f of x is plus phi of x, where alpha satisfies and phi is small. So what's called a perturbative case. So assuming all this, you analytic. Kind of, you get the C1 thing and you get everything already. So it's as good as it could be. So in this situation, we say that the dynamic, let us say, of F general map reduce. So that's why how the name reducibility appears. Reduce entirely. So you have a simple change of coordinate that preserves the regularity class to the simple basic translation. So the basic quasi-periodic motion. Okay, so that's kind of one prototype of this reducibility theorem. And what I need to explain just this thing here that I didn't say. So what satisfies what? Here it is so-called condition, which means that so the Diophantine condition is the following: is that if you look, so it the case that alpha is not too close to a rational number. So it should be, so a rational number is a number that is of the form P over Q. So it says that if alpha, and then there is a rational number P over Q, it's always non-zero in some kind of, so if it's irrational, it's always non-zero. But now it's going to be non-zero in a kind of definite way. It has to be bigger than some constant to some power here. So there exists constants T and R such that this estimate for non-zero. So so if you have this situation that you are far from the rational numbers in kind of this quantitative way, you say that you satisfy the Diophantine condition, and under this hypothesis and in a perturbative setting, you get this theorem of Arnold. So that's kind of prototype of a reducibility theorem. Now you may want, so what was I saying? That like this, you immediately don't like this condition. Like this condition is kind of maybe why do you need to put something that well, most numbers, then you analyze, most numbers satisfy some Diophantine condition in the sense that almost every number according to Lebesgue measure satisfies it, but it's not true, for instance, for a generic number according to this. According to Baire category, this defines a meager set. Like so, a generic number is not Diophantine; it's Liouville. It's very well approximated by rational numbers. So, but even if you care about just about almost everything, you would be better for the beauty of the theory if you didn't need to discard those, like this in principle small set, but still interesting to describe. So, but the point is that you cannot get rid of this because it can be shown that even in a perturbative situation, if you consider in general what's happening, so if alpha, so I didn't mention something here, it's x plus alpha, and alpha is the rotation number of alpha. So, but anyway, so even if you have this perturbative situation, you're not going to be able to do much better, to do better than this kind of homeomorphism. So that was like there is example of Hermann, for instance, where where h is not an absolute continuous function that would be weaker than C1, but then it's not even absolute continuous. So even the measure theoretical structure of the circle is modified by h. So anyway, so in which direction you can move. So I mentioned in this particular case, the next step of the theorem was the theorem of Hermann. So it removes perturbative condition, and it needs a little bit more here than to get full. But Hermann has already something that was a full measure condition. Then there is a discussion about what's exactly the optimal condition that's necessary to put here. So that is known that for kind of theorem of Arnold becomes some condition that's kind of called Bruno condition. And then there is in the situation of Hermann something that's called the Hermann. But anyway, it's kind of, there are those refinements. But so that's one example of initial discuss here is that this condition that you have, it's not it's measured theoretically large. It's not a condition that's stable. It's not an open condition because like there is the generic set that that's bad. And sometimes it's annoying to describe what's here is kind of everything's kind of very well clean because you have, but in other situations you get in some kind of a messy condition. Like you'd like to talk about some system and talk about some property that's stable, that remains true under perturbation. That's kind of more convenient and a more elegant way to deal with. And it would be good to have some description that includes this, but it cannot be covered by this kind of reducibility description because it's really necessary to put some extra hypotheses that have only measured theoretical quality. So that I'm going to describe then a concept of that's going to be useful, but I'm going to show that how it is important. I'm just going to describe in the situation that it has so far. So substantial advancement. So I'm going to consider some kind of related systems, like because this was just an example. So, but you can move in many directions. For instance, you can go to higher dimensional generalizations and things like this. I'm going to do a very specific situation that with has that comes from some motivation from some theories in quantum mechanics. So so you have the following systems that you're going to be interested on. So it starts with some operator on this space L2 of Z, and then you have a linear operator of the following form. So it acts as an operator HU n. So it acts on a sequence, and then the nth term of the after you apply the operator is given by this following form. It's so basically modulo the diagonal term is basically a discrete Laplacian. So you take the near neighbors, and then you add something that's a diagonal term interaction that has some potential. So there is some Vn here. So it's basically, if you imagine that it's just an infinite matrix with ones just off diagonal, and then there is this Vn here, Vn, Vn plus 1, and so on. So you are trying to understand this kind of operator. But where Vn has some kind of particular, and then you look at form of Vn that I'm interested here is produced by some quasi-periodic sequence. So it has the form n alpha, let us say. Want to kind of get closer to some x plus n alpha here. So here V is a function on the circle, which would be regular, and then you have this kind of case. So if alpha is rational, then this is going to be just a periodic sequence, and if alpha is irrational, it's going to be a more general quasi-periodic sequence that you're going to get. So you're considering this situation, and the motivation here is that this operator here, once you is going to be important to understand the dynamics of something model. So the actual quantum dynamics that appears here is for the unitary evolution. So that's actually the dynamics going to appear, and you are going to be interested in what happens. So here, right, is so UN is a unit vector, right, in the Hilbert space. It's going to be the amplitude probability particle somewhere in Z, right? So where you could find it, but to represent it is of course given by this complex sequence that and the evolution. So you apply here. So you start with a vector u, and then you let it evolve by this unitary semigroup. So, and basically there are several situations that are going to show up. So that the qualitative different dynamical features that may appear. So just to give an idea, I'm not going to talk about the quantum dynamics. Sometimes there is the phenomenon of localization, where suppose that particle, so here is Z, but I draw like a line. So particle was somewhere here, let's say, that I knew that it was located, there was this amplitude probability, it is somewhere, right? So the probability, so it adds to a probability function in Z, so the probability to find it very far away is small, of course. And then you let it evolve with time, and you look at where can you find this, this object. And it might happen that and then start finding it very likely far away. So the particle is like moving, or getting kind of dissipated in your space. So it could imagine that it, or it becomes kind of very little concentrated deposition, and then you don't find it in the specific part anymore. So this would be a non-localized motion. Localization would be that well, it moves a little, whatever, but it's still with large probability. I locate it in a single in a specific region. So this kind of localization phenomena would be read at operator. It just so localization, let's say, corresponds so this means that this operator has a basis of eigenvectors. So of course, eigenvectors, but in general have a spectrum, but you may not have eigenvectors, or just have something more general. So if you have just a basis of eigenvectors, then you can see that you cannot kind of get this spreading phenomenon. And there are other situations. So then you can corresponds to when you have some kind of atoms in the spectral decomposition or the spectral measures. Atoms kind of motion so things get dissipated very fast. So that you have very large probability of finding things kind of further apart. And this is covered in something that instead of being localized, things move to infinity. And this corresponds to something that's kind of a ballistic motion, that's kind of faceted. So basically, one thing that you have is that you don't have this. You just have this kind of Laplacian. Then things just kind of evolve very fast. So you get this situation of absolute continuous spectrum. And if you didn't have, then you have just the diagonal term, so it would be this point spectrum, so you'd have localization. So if in front, then you imagine you will prevail. Get this kind of motion. And of course, a kind of dividing everything by lambda doesn't change the quality of the spectrum. In front of this, imagine imagine that you might be closer to a localization situation. So you could imagine that this that there should be an oscillation that evolves from small to large potentials. Okay, so that kind of in general, but so what's the relation to the dynamical systems? Where's the up here? So if you try to understand the spectrum, even if you don't have a point spectrum, you can look at trying to solve this equation, the eigenvalue equation in principle, and try to look for solutions of this equation which are not necessarily in L2. So that's generalized solutions of this equation. So how do they look like? It turns out that you can write it in a matrix form, in the form like E minus Vn minus 1, 1, 0, applied to un minus 1 equals un plus 1 un, right? And then basically if you have just, you know where is u0, u minus 1, so there's a two-dimensional space of possibilities here, and start applying this kind of sequence here, v0 minus 1, 1, 0, minus several times, and then E minus V n minus 1, 1, 0. This is going to be un plus 1 un, yes, hopefully. And then, so you see that to see how is it behaving far away, you just apply the sequence of matrix here, right? And how is this sequence of matrix? V0 is what? Is V at x, and then this is V of x plus n alpha. So you're applying along this. So to capture this, you write a dynamical system with the following. It takes w and takes to x plus alpha a of x times w, and a of x is this matrix. Let's call it y because x was something else. A of y is E minus V of y minus 1, 1, 0, right? And if you start iterating this, so you are going to have, in this coordinate, you're just going to get exactly this the same product that's appearing here, right? Because at each time you're kind of moving in that direction. So you're trying to understand this. Where does this take place? Well, here you have a circle. Here you have some kind of W that you may imagine that's a vector in R2. But to get a picture, you can, of course, take the projectivization of this coordinate here. So you get another circle. And then you have two circles, and then you get a torus, right? And the torus, basically, you have something over the first coordinate. It's just kind of moving normally here by x goes to x plus alpha, and the other is doing a little bit more complicated, acting by a projective transformation. And in this setting, it's no longer one dimension, but you could kind of think that you can you have some similarity to the circle. And indeed, if you consider the regime, particularly in the regime where V is small, it's going to be very close. So let's assume that, so the spectrum, so if V is 0, then the spectrum is minus 2, 2, right? So for V equals 0, this is the spectrum. And then, so let's look at things that are more or less in minus 2, 2, so that this disappears. This, you're going to have always the same matrix, and this matrix is going to be just, if you're inside the spectrum, it's going to be an elliptic matrix. So the trace is smaller than 2. So up to a projective change of coordinates, what you have happen is you have a translation here, and the same elliptic matrix in this coordinate. So elliptic matrix is after change, it's going to be just a rotation. So you have a rotation in both coordinates. So basically, so if you take E belongs to minus 2, 2, then this becomes just a translation in both coordinates. Then it becomes just a translation of T2 now. A similar situation, just one dimension, right? And then it is true that you can apply KEM theory in a kind of a little bit more complicated version than what you had before, to say that there is a trend, because KM theory is not that theorem, just the theorem that I talked about. No, there's a general bunch of techniques that describe a situation where you start with some quasi-periodic motion, and you add a perturbation, and the quasi-periodic motion persists, but under a few conditions. So the big work is always on this condition, but what I mentioned, there is some kind of perturbative condition, there is some regularity conditions, and there is also usually some kind of measure theoretical condition, usually linked to conditions such as this one, that are related to kind of avoiding issues of coming from rational numbers that are called resonance and so on, and encoded in so-called small divisors that appears when you try to solve the equations that several approximated equations that are going to appear. But you are in this setting when V is small. We are close to a situation where you have just a translation of the two torus, and you can ask what kind of persistence there is. And there is a whole theory about this. And then I can state some. In this situation here, because this is a fibrate dynamic, there is a topological theory that's going to say that there exists, so general theory will say that there exists a translation, a rotation vector which now has two components, alpha, beta, right? And the general theory, so it was put in this form, I think it was Herman that formulated like this. You just apply directly the KEM theorem, one of the versions of the KEM theorem, and then if alpha beta is kind of alpha beta and is a two-dimensional version of the condition that was written here. If alpha beta is Diophantine, then and in the perturbative setting, here is things by Herman. Perturbative setting, the system is reducible to the so he proved this, but he also proved in the same, so this I'm talking about a paper from beginning of 80s in Commentary, but he proved this, and he also showed that cannot get rid. It's not like for the circle of perturbative condition. Okay, so that this is also something that's happening. Why? Well, it's because so basically, he showed that, so this kind of thing here. This, well, yeah, some kind of, yes. I'm going to give a.
But you always expected some condition as to there, or not?
Well, for the circle, you don't need, like anything that you just need to have the condition on the rotation number, and then you win. Here, like there is a condition on the rotation number that works, the rotation vector, but it's not going to be enough. Why? Because he showed that he considered, for instance, the following situation: v of x equals 2 lambda cosine 2 pi x, example of a function, and your lambda is bigger than 1. And then he proves the following. But this, so here. Iterates of this function, so the matrix x, right? So this is a matrix, so it can be large, right? Look at the norm, and then you look at it at exponential, because you're multiplying. So you take log, you divide by n, right? And you look at the average behavior. Has a limit. Additivity. And if you have quasi-periodic motion, the motion here is kind of a kind of elliptic motion up to change. So what you get as the products, they remain bounded. So this gives 0 necessarily. So so what you have is that if motion is quasi-periodic, then L equals 0. Lyapunov exponent is 0. And Hermann discussed how if bigger than log lambda is bigger or equal than log lambda, and then it's positive. So under this condition here, so if you are sufficiently far from constant, this will happen. And so I mean perturbative. It's not just a perturbation. If it's far away enough, then something else starts appearing that was not appearing before. That because when you are to rotations, at least under this Diophantine condition, you have reducibility, and then the Lyapunov exponent is 0. But now far away, then Lyapunov exponent is positive, and then reducibility must fail. So it's a little bit more complicated situation. Okay, so you have this. And then I didn't ask how much time I got in total. Okay. Yeah. So what happens here, you kind of get interest on trying to understand exactly where each kind. So what's the goal of the theory then? So there is a theory remain reducibility here. And you know that the theory doesn't describe everything. So the theory is kind of more complicated. So ideally, you are going to try to understand as much as you can about this reducibility region, and then you have to understand how it fails, why it fails, and whatever there is. So there is this kind of post-Lyapunov exponents that are influencing things, and maybe there are some other things that may happen, and you try to understand the whole picture that you can path. So in principle, there are a lot of things, but then there are a few theorems that are on this. So one progress is first to get rid of this condition. Okay. So what's this reducibility good for? Once you have this reducibility, it's just generally understood that it's linked to you get to the situation, you are reducing to the situation where the matrix is constant, where you saw that the situation when v equals 0, which when you just have no potential, you just have the Laplacian, as I said, that you have absolute continuous spectrum. So basically, in the theory, when you apply to quantum dynamics, there is a general principle that reducibility relates to AC spectrum, and a little bit more complicated. Point spectrum and localization. Regarding this thing here is that if you have an eigenvector, then is kind of a solution un that's kind of L2. So it has to decay in the future and decay in the past. So what it means that you have a vector here that when you apply this matrix, it gets small. So for you to apply matrix, the matrix are in SL2R. They have this determinant 1. So if you have a vector that's getting small, it's because the matrix is getting big, right? So you have to have growth of matrix in order to have localization. And if you want things that kind of that decay exponentially fast, so solutions here that not only L2 but are exponentially fast, you have to have exponential growth, so you have to have post-Lyapunov exponent. So you have this kind of thing. Anyway, a series of theorems. So for instance, you have Liason theorem. It says that suppose that alpha is Diophantine, and then in perturbative situation, then you have pure is absolute continuous. So what it means that what's the counterpart is that so that we cannot prove that the system is reducible. Okay. So more precisely, so let's try to precise this. So he shows that the system is reducible for all beta satisfying some arithmetic condition of full measure. So you could imagine to DC, but it's a little bit weaker than this. But this would be fine for us. So it looks like the same, but except that there is a difference in quantifiers that's very important, because the quantifier for beta happens after. Here, you first shows the reducible situation, and then you change the other. Let us focus on like there is again this issue here that's that full measure condition here. That's very annoying for this statement. But actually, he proved more. So I can put another statement that kind of clarifies the situation. So that's when this concept was introduced, as far as I am concerned, by this theorem of Eliasson. He proved a nicer theorem that's better, that allows you to understand everything better. Is that those guys where you don't satisfy these arithmetic conditions, at least with respect to beta, you can always say something dynamical. Because so far we're giving up. After something didn't satisfy the arithmetic condition, you just forget about it, and then you describe the guys with arithmetic condition. But here he's going to be able to say everything. So come back to Eliasson's theorem. So Eliasson. So let's assume something about alpha to start with. So alpha is DC. You have perturbative situation. Then for all systems, so now the parameter that appears here after everything has been fixed is the energy. Like I was talking about beta, we can talk about well, for everything, for all systems, goes to constants. So in all cases, you have almost reducibility, with a concept that I'm going to describe right now. So what it means? So what's reducibility? It means you change coordinates and you get what's this change of coordinates? I can write like this. You have a matrix A of x, and you make a change of coordinates that depends on x. That's kind of by a mid. So you have to apply a change of coordinates here, and then you have to conjugate at the next step. So things apply. So that's the natural way to do it. And then reducibility means that this becomes a constant. It's going to be a constant. So you change your coordinate. So the coordinate depends on x. And since the variable is moving in the base by x goes to x plus alpha, it looks like this. And says that after change of coordinates, I recover the constant matrix. So this is reducibility. So essentially what he showed is that you may this may not be always possible. So that's kind of clear that there are some kind of resonance that that appear when there are some in the second variable when some things happen that block this. But so he understood it as well. What he shows that there exists a way to approximate this. So there exists a sequence Bn such that Bn of x plus alpha, there's a sequence of changes of coordinates which allow you to approach a constant as much as you want. So you can get closer and closer to the constant situation without ever succeeding. Like, because this converges to a constant, but the Bn's may diverge. So they can go to infinity. In general, they do, but you approach as much a constant as you want. And then what's going on here is that once you are close enough to a constant, you can think this way. Then you can apply the general theorem, because once it's closer to a constant, there is some kind of general KM theory that would apply. And then it clarifies here the roles of the quantifiers and everything. And the advantage of this statement is that I didn't need to make any further measure theoretical thing regarding beta. You're probably not very impressed because I still have some condition on alpha. And since I am out of time, so there's then a bunch of advanced here done much more recently. Let me just say the general theorem that appears so eventually you have that so there is this theorem here. Let's assume now that V is small. So let's say so it means that there is an open set. Like I like to refer to this in kind of stable situation, right? So the neighborhood of constants. So constant potential, so that for V, so neighborhood U, so that if V belongs to U, right? So if you are in this neighborhood, so that this is in a setting such that then for every alpha irrational well, for everything there, you always have almost reducibility. Right? And once you are almost reducible, as I said, you can kind of go arbitrarily close to constant and apply whatever theory you have to describe things close to constant. But now you have this new concept that you can see that it's open, right? Because if you start something that's far from constants and it's almost reducible, you can conjugate it near constant, and then everything's almost reducible now because of this theorem. And then there will be a neighborhood of your original system that's almost reducible. So you get immediately a concept that implies that almost reducibility is stable. No more need to be talking all the time about some kind of measure theoretical condition. There is an open condition, which means that R is open. Right? So it's kind of a very much advantageous situation to describe what's happening. And then the goal of the, and of course, if you are in this situation here, you can prove that, well, of course, but you can prove that in this situation, when you are in this almost reducibility region, you get this kind of AC spectrum, and you describe everything. But anyway, the goal of the theory becomes try to understand exactly what's the size of this region. So now, instead of talking kind of vague terms about what leads to a absolute continuous spectrum, because this it's not a statement about a single point, you cannot talk about reducibility because it was never open to begin with. So you could not talk. So you have something that is reducible, and something nearby is not anymore. But now, what about this concept? It's an open set. what's the extent where it is where it holds and why it ceases to hold. And just now, if I want to mention anything beyond that, I will not have time, so just mention the theorem that clarifies the theory is the following, so that the situation is, so I look at the general situation where you have alpha x, so x goes to x plus alpha, and w, so x, so it's xw goes to x plus alpha, a of x times w, and a is analytic, right? So you can describe this the situation as follows. You have some region where the Lyapunov exponent is positive, right? And it's a little bit more complicated. Or set of things that are important that relate to spectrum and so on. But just without getting into all this, theorems like this Raman theorem, where the Lyapunov exponent is positive, which is called the supercritical region. There is some kind of region here, kind of perturbative region. Whenever you are close to constants, right? There is this theorem that says that you are almost reducible. In particular, so almost reducibility already that Lyapunov exponent is 0 because you change coordinates, it gets closer to constant, so it cannot grow much because it's a constant, and then Lyapunov exponent has to be arbitrarily small, so it's 0. I'm avoiding the issue of that the matrix could be hyperbolic because it's not important for spectral problems. But anyway, but forgetting about this kind of annoying thing that allows you to, needs to be dealt by selecting some fractal subset, there is this region here that's called subcritical region, which let's say the Lyapunov exponent is very 0. The actual definition is the following. So this means, so this region, matrix growth is exponential, and this region here means matrix growth is sub-exponential. Well, then it should be just a partition of this, but then a little bit more. Not just
These regions are regions in the space of matrices.
in the space of functions. So A is a function from torus to R. So that's kind of a region. So you have a general. It's sub-exponential, but like everything was real. But things are analytic, so they extend to the complex plane. So it's sub-exponential not only for when imaginary part is 0, so when you have real, you are iterating the real guy. So you can go a little bit to the complex plane, and it remains 0. It is true in this situation here because everything extends to a neighborhood of the real line, and then you still have kind of low growth in a neighborhood. So that's coherent. So so you have these two things, and of course there is some kind of things in between that should be the guys that sub exponential growth. Well, after you have some kind of preliminary theorems, but you cannot go. You go complex plane, it is exponential. And then there is a theorem that says that thing here is given by there's no nothing kind of serious in between. There's no open set. There is nothing big. In fact, it's going to be given. So this critical region is contained in a complex codimensional countable union. Codimension 1 submanifolds. So there is some kind of things here by solving solving some analytic equations here. Everything has infinite dimensions, so that, but there appear some equations here. You solve whatever equals to 0, gives some equation, and whatever. But just by kind of this kind of tiny sets, it will separate like this. Ideally, you would like just some region here, single equation that kind of. Yeah, it's a little bit more complicated what you can prove here, but that's good enough for applications. Okay, so then this theory gives you, well, there is this part here that you know what's happening. And now there is this part here where you know that Lyapunov, and this part here becomes pretty important because this is something. Here's small, here's everything else, and this everything else is described in terms of growth of matrix. So that's not a condition of smallness. It's not saying that the matrix is close to constant. It's just saying it doesn't grow very fast, right, in the complex plane. And the fundamental theorem that I have here, that's the hardest theorem in this theory, is the so-called almost reducibility conjecture, but it's proved, which says that almost reducibility. So everything here, that's a big region, everything here is almost reducible. And then if you want to clarify, understand more precisely, okay, if there is some measure theoretical condition on the small divisors and whatever, you get out reducibility. But that comes after, and then that's kind of much better understood. So that the big steps to show that under this open condition, this is possible to show that's essentially open, that it is enough to get almost reducibility. So that's kind of a complicated theorem that needs to be proved. Okay, so that's kind of the first, I'd say that it was taken essentially to the end, first success of this theory of almost reducibility. Let me just, since I have no time, let me mention that the theory keeps being developed. And let me just, like, since I don't have much time, so what's going to be given for the case of the circle? I could do more, but I will just do a comment about the situation. This is we have had some advance now. What's known for diffeomorphs? You can ask the same thing. The Lyapunov exponent is 0. But if you look at imaginary part positive, it becomes positive. So just at the real line, it's sub-exponential, but in the complex, it's never. Well, the matrix are SL2R matrix. So in this region, in the end, so with that theorem, you say that if the Lyapunov exponent is 0 in a neighborhood of the real line, you can change coordinates so that it gets closer and closer to a single SL2R matrix. Is it? Well, there are totality issues. You have to have parameters that kind of go transversally to this region. You know that. What do I know? You need to have derivative of this. Such that the, let's see, well, you don't know what those equations are exactly. Sometimes I can compute them approximately, but you don't know a priori if you have a finite dimension. You could have something that lies exactly this. This is given by one equation if you're kind of unlucky. Of course, a generic family intersect transversally, right? But you cannot say, there's no single formula that gives you that whether you are transverse or not. I can compute in some situations, but it's better to state the theorem in infinite dimensions. Okay, otherwise there are equations, and the equations are what they are. So that in principle they don't have a nice form. They are very complicated. So in some situations I can compute what are the equations. So I can analyze the situation that's close to that view of x cosine x. Then I know more or less what's the equation, and I can give conditions that give transversality. Anyway, so just about diffeomorphism of the circle. So there is the following theorem. So that's what I'm trying to write with Rafael. So that says that alpha is nothing but alpha, because that's not. So f is is orientation preserving map, but just C infinity this time. Any map and a smooth map, then F is almost reducible. So which means there exists a sequence Hn, what's C infinity, and such Hn minus 1 of F Hn converged to x plus alpha in C infinity. And arbitrarily close to him. So that's what we proved. And we are trying to understand things that are happening in larger dimensional situations. So for instance, maps of the annulus or things like this. We are regarding this, there are some kind of different problems related to actions of commuting maps. Also, it's interesting, you can have not a single diffeomorphism, but several diffeomorphs under some commutative condition. But like something negative as well, in the case of analytic map. So you could, so here I'm doing C infinity. What if I put analytic here? So this theorem is not true in analytic class. Because, why? Because when you have this situation, if you have almost reducibility general fact, it means that the situation reduced the situation. Because you're very far away, then you can get constants, and then you apply local theory, and then the global theory is the same as local theory. And for analytic maps, it's not true, because the global theory is different from the local theory. Because, so what you have is that there is the problem of analytic linearizability, analytic linearizability, or reducibility, as I'm writing here. As I said, there is some kind of arithmetic condition. I said that people were describing what exactly is this arithmetic condition. It was very complicated and so on. So you know that the local problem, so there needs some arithmetic condition. In the local case, the Brunner condition. Called the Hermann condition, 8 condition. Otherwise, you this to that. So as I say, but in the C infinite category, we succeeded in proving that it's actually almost reducible, and you have hope that this will extend to some situations that are of interest in some conservative dynamics in higher dimensions, and also for actions in the cell. So, but this is still not completely done. This theorem is already, we checked it completely, but you're still working. But we hope that this concept of almost reducibility that gave such a good picture for the problem of Schrödinger operators of quasi-periodic type will kind of have more applications in low-dimensional dynamics of near this kind of in the extending the setup of this KM theory. Okay.
Thank you very much. Thank you very much. I think it's time for a few questions or remarks, if any. Any additional question or remark? May we use the mic?
Yeah. This option between the subcritical and the supercritical can also be related to dissipative and conservative, since you have a positive exponent, Lyapunov exponent in one side and zero on the other.
Yeah. Well,
can you look at that as an entropy in one side and conservative on the other?
Well, the Lyapunov exponent positive, this dynamics, the dynamics that I wrote in the tutorials, it is it always has zero entropy because it has this fibrate form, and then there is no space. Like in general, in the two totals, you have dynamics that may have positive entropy. It relates to the fact that the action on each fiber can be kind of much more complicated than that. So sometimes people in the post-Lyapunov exponent region, people talk about some strange non-chaotic attractors. So the kind of dynamics that you get, it does get very thing, but still it doesn't generate entropy, but the behavior on the fibers, it is exponential. So there is some kind of exponential variation between fibers without producing kind of entropy, because things are still pretty much ordered in space. So there is, in the positive Lyapunov exponent region, the analysis of the dynamics is very close. So the best way to describe the dynamics is close to methods like that appears on in one-dimensional dynamics for kind of interval maps with positive entropy, that appears for some two-dimensional maps that are very difficult to understand, like the Enont map. And so that there is this whole situation that's kind of difficult to describe. But same phenomenon is appearing here, which is usually described by interactions between exponential contraction and exponential growth, right? And without having some uniform angles between this. So everything's related to some kind of homoclinic tangencies and things that are tangents between stable and unstable directions. So this region here is really kind of, you try to understand with techniques that have been developed for understanding this kind of non-uniform hyperbolic situation. And here is kind of this understanding of subcritical region is new, because that's kind of a new condition that's kind of comes from the complex plane, and you try to use this, the complex methods are fundamental in this description.
Any other remark or questions? That's fine. So perhaps we can thank the speaker again. Thank you very much.
Let's try to. Sí.
Era bom levar já os papéis para não...